I'm going to introduce our speaker, and we do have a change of name today. This is Martin Doig from Neodrill. He's going to be joining us. And I'm going to invite Malcolm Banks, who's the Well Solution Centre Manager here today as well. So, Martin, can you just tell us a bit about yourself?
Good afternoon. I have been involved in the drilling industry since way back in the 80s, which seems like a long time ago. I've been involved with operating companies and service companies in that time, and I recently got involved with this company, Neodrill, and that's where we can...
Great, I think, perfect. Well, we'll look forward to hearing some more then. Malcolm, can you tell us why it's relevant to the OGTC?
Yeah, sure, Rachel. I mean, obviously, reducing well construction costs is a fundamental sort of criterion direction why we're trying to do here in the Well Solution Centre. And top hole drilling has historically always been quite challenging and quite risky, and has high costs and high risk associated with it. So obviously, the principles of the way it's been done has changed very little over the last sort of 40 years in the North Sea. So obviously, we're looking at ways that we can improve on that and different ways of creating that well foundation. And this type of technology is a great example of that.
Great, perfect. So before I hand over, if any of you are on social media, feel free to share #TimeToTech20 and tag us in and we'll share your post. So it's over to you. Your 20 minutes starts now.
Starting now. Thanks very much. You know how cold it's been the last couple of weeks? Remember the night it snowed a couple of weeks ago? Temperature plummeted to about -5. Boiler broke up. Boiler in the house broke down. That's it. Finished. We had to revert to heating the house in an old tech way. We'd lost the smart tech way, had to heat the house in an old tech way. So you're back to things like contemplating how and what you're going to do as soon as you step out of your nice warm bed in the morning, especially when it's -5. So you have to think, what auxiliary methods have you got? Have you got electric heating? Have you got a gas fire? Have you got coal? Do you need to go and get some wood from the shed? You can handle it. My teenager couldn't. He's never lived in that kind of old tech world. Effectively, you have a method of heating your house that's the smart tech method. You wouldn't want to go back. Thankfully, today is B day. We get a new boiler today, so it's back to living in the real world. The conventional old tech method of drilling a well, of spudding a well, is fairly complex. There's a number of steps that you need to fulfill. You have to have a competent rig plan, well plan in place. You have to hire a rig. You have to tether the rig. You have to get it in the right place. You have to handle big pieces of equipment for the BHA. You have to get that BHA together. You have to get it to the seabed. You have to drill the hole that you want. You have to then maintain that hole, deal with any problems that you might have had when you're drilling. You then get the BHA out of the hole. You then start putting together the even larger and more cumbersome pieces of the conductor equipment. You have to put that together, run that to the bottom of the hole, and then you try and stick it all in place by pumping cement. And you rely on the cement coming back to seabed to ensure that you have a good foundation for the rest of your well. Meanwhile, you're observing the weather, and the weather can disrupt all of this at any time and cause massive delays, which isn't good when you've got an expensive rig that you're using. This process has changed little in 50 years for subsea wells. The intrinsic hazards contained in each of these processes can delay or halt progress at any stage. Indeed, delay in some of them being achieved can prevent the successful completion of the intended goal of providing a strong and stable foundation for the well, which will prevent or delay at great cost deeper progress in that same well. I want to talk to you today about a smart tech option which is the Conductor Anchor Node, this is a big representation of it, and here's a smaller representation of it. This is Conductor Anchor Node is shortened to CAN technology. It looks like a can, obviously, and it provides a smarter well foundation. It's designed to replace the old tech method of subsea well foundation It's deployed from a vessel prior to the rig arrival, and it dislocates the operation from the rig operations and the subsequent well plan. So you can put this in place weeks or indeed months before, and then you can turn up and drill out 17.5-inch hole or whichever hole size you want to drill ahead with. It employs it's lowered to the seabed, and it employs the suction anchor principle, which is a long-used method of securing, tethering objects to the seafloor, but not in well foundation until this point. So here we have two cans, and it's important to understand the dimensions of these things. This one here, I like this picture better. This one here is in northern Norway, a place called Ripafjord, which is up near Hammerfest. It's about as far north as you can go in Norway. This is the can here. The can is 6 meters diameter, which is the width of the screen. That's very handy. So it's a 6 meter diameter, and the height of the can can be up to 17.5 meters. If it goes offshore with the conductor in place, you can see the conductor, which is cemented in place here. The cement's been painted over, but it's cemented in place. This one's in Australia, and this one is, as you can see, horizontally secured on deck. They're both heading out to be deployed. To give you an idea of the dimensions, think about this. If we took the conductor out of there, you could drive an articulated lorry inside that, and it would be totally enclosed, lengthwise and height-wise. They're big objects, and that's one of the things that people sometimes struggle with. They're designed to be easily deployed. When they go over the side, an ROV pump is used. When they go over the side and landed on deck, an ROV pump is used to pump out through the hatch the water, and the structure penetrates the seabed and settles to a position that allows us to make progress from there. The major benefit of deploying such technology is that the rig is not required to be on location to spud the well. This removes a major source of uncertainty and the greatest cost from rig construction. The project's success is then subject not to the vagaries of the weather and the rig's abilities to handle large equipment and drill the initial hole size, or maintain that hole, or handle and run the large conductor pipe, or where you might end up with a cement job. It's now ready for the rig to turn up and drill ahead. Oh, excuse me. So, as I said, the important thing to think about is reliance on a steady foundation for all future drilling. The pre-installation of the can provides for the secure well foundation before the rig arrives and allows better control and understanding of the future fatigue management by providing a predictably solid base, because you've put the cement level in before you take it offshore. This allows you to be able to predict more certainly the future capabilities of the well. In this way, the can design provides better axial, lateral, and bending moment for the well foundation, and thus ultimately the most controlled fatigue life possible for the well. Often the old tech conventional method encounters operational issues, leaving the conductor in an unsecured condition, as you can see with the video is finished now, but the movement of the conductor, where we would really like the cement to be up to here and this not moving at all. The can on the right is the conductor, and we have developed this further, but this is the basic method or system that we have at the moment. We can take this further to allow production facilities to be added on if they're required. But a conductor would be run for exploration wells, and probably a can integrator would be run for production wells. So use of the can in well construction improves the safety aspect. Requirement for lifting and manual handling, as I mentioned, is now avoided. Large bottom hole assemblies and conductor components, such as you can see, are difficult to handle. and they can cause major problems if mishandled. In this case, we have caused major damage, possible injury. There could have been multiple deaths in the doghouse here, and certainly in this case, certainly costly delay to operations. In addition, there's more assurance of better control of inclination issues, as during pumping progress at installation, the bullseyes are monitored by the ROV. It's really important that the foundation of the well is vertical, and it's more assuredly done with this method. Waiting on weather can still be an issue, but the meter runs much slower on a vessel than it does on a rig. In addition, there's a reduced environmental footprint because you don't have the rig on board, the rig on site, so there's less CO2 produced. And also, you're drilling a smaller hole when you run a can, so you have less disruption and distribution of cuttings on the seabed floor. So here's a representation of what we're So what about the track record? There's an increasingly impressive track record. We've run 20 cans worldwide, 17 in Norway, 2 in the UK, and 1 in Australia. They've been run by 15 major and minor operators. They, on average, save 2 to 4 days, but in addition, the average amount of time that we save is, the average amount of time that the vessel is on site is 22 hours, and the number of hours required to install a can is about 10 hours. The average installation inclination for each of the cans is less than half a degree, which gives great assurance for future progress in the well. Sorry, I'm just making sure I've got my right notes here. The lowest enabled kickoff, which is an issue for shallower reservoirs, is 10 degrees. So in 2017, a joint industry project was set up to enable the demonstration of all phases of a full can deployment. And the project included looking at engineering, planning, and deployment operations. Participants consisted of 3 distinct groups: the UK authorities, in the case of OGA and OGTC, oil and gas operating companies and service companies. UK authorities were represented by OGA and OGTC, and they went through all of the issues that were covered in the that were of concern at the across the industry. So we looked at the operating envelope and the deployment schedule and methods. The final part of the study component was the capacity and fatigue. And the conclusion from that was that this method would be a significant improvement compared to conventional conductor soil interaction models. This was brought by a third party, by 2H, in their global riser analysis for Siccar Point. There were, along with Siccar Point, there were Maersk Oil, Nexen, Shell, and the service companies were Technip, FMC, and Baker Hughes. So with regard to the Siccar Point field trial, their fees were waived, and they were running one. They were running. The reason for that was they were running a can in the Camo West of Shetland field at the start of last year, and in return for involvement, they made available to all joint industry project members all of the documentation. So there was a clear view of the success of the technology to all those who were involved. The field test experiences can be summarised as follows. The can was successfully installed west of Shetland in 1,100 metres. The well was spudded with 17.5-inch BHA, and a successful as-planned drill-out was performed by the rig without incident, showing this to be more of a perceived risk than a real one. The conductor was considered as an important enabler for more efficient drilling startup of a cold-stacked rig, as it greatly simplified logistics and BHA handling by not having to drill a large borehole. The installation fulfilled all technical commercial objectives in showing the advantages of CAN technology in deeper waters. As all JIP partners had full access to all Camo 6 CAN-related engineering planning and execution reports, the CAN experience gap was successfully closed by this field trial of the technology. The purpose of the JIP was to improve the end-user confidence in CAN technology as a generally fit-for-purpose well foundation for most types of seabed soils, with a novel top-hole well construction method ensuring a quality well foundation for subsequent well operations. This was achieved. CAN technology enables the removal of a complex and potentially hazardous process from the rig schedule. It delivers a simple, smarter well foundation from a vessel, allowing the rig to turn up later and get on with drilling and completing the well from a more assured base. The greater fatigue management assurance and the ability to pre-install production modules allows the operator to plan for the future rather than worry about the past. The future development of this technology will allow planning and accommodation of the required facilities on board the smarter well foundation CAN to maximise the returns by minimising the delays of production installation and getting to first oil. The CAN integrator is a single well template. It facilitates offline installation of top hole section and also Christmas tree if needed to reduce rig days and project execution time by potentially removing costly operations at both ends of the drilling process. These cost and risk reductions, in conjunction with the integration of post-drilling facilities, will provide opportunities to unlock smaller exploration and development opportunities. Thank you very much.
Thank you very much, Martin. We are now going to open up the floor to any questions. If you've got a question, just raise your hand and Mario will pop over with a microphone. Quiet group this week. Oh, here we are.
There's one over here.
Dave Wilkinson from University of Aberdeen. So when the can's being placed on the seabed, and it sinks down a bit. How do you ensure it stops sinking at the right point so that the top of it's just on the seabed surface?
There's a lot of work done up front in terms of the core penetration tests and the actual sizing of the can to ensure that the correct dimensions are applied.
Oh, I see. The length of the can will determine on the seabed conditions.
Yes.
Oh, right, yeah.
Yes.
Oh, I see, right, yeah. Okay, thank you.
No problem. Thank you.
Okay. Any other questions? Yep, over at the back.
There's one behind.
There's a couple.
Hi, I'm Kirsty Langan from Apollo. You mentioned that you've had 20 installations so far, and obviously this can be used in a million different conditions, but how do you see it rolling out? You know, how are you planning to grow this to the next stage? Do you have particular areas you're focusing on?
The limiting factor is at the moment is really the soil hardness, and if the soil isn't soft enough, then that can be an immediate limiting factor. In terms of rolling out, the company has focused on the Norwegian market predominantly to date. I'm the first employee I'm the first employee in the UK. We have a real focus on the market here. I think there are real applications west of Shetland and elsewhere where this could be used. But beyond that, in other basins around the world, there are great potential. At the moment, we're only manufacturing in Norway, but there are opportunities to manufacture elsewhere in the world. And manufacturing is a big concern because of the dimensions of the if you can fit an articulated truck inside it, if you try and put one on top, then you can't really take it anywhere. You can't go through bridges, and you have to close down roads and things. So we have to manufacture at quaysides and things.
And the other thing I was going to ask you, maybe related to the soils point, where do you see the next phase of the technology with this going? You know, design-wise, what do you think are going to be the sort of upgrades and the developments that you make on it?
Well, really, they're on the integration into the production side to anticipate and reduce as much as possible the time between drilling and completing a well and bringing first oil. So it's being able to integrate as much of the subsea technology that we can into that firm base that we're providing. And there's a lot of work being done on that already. Thank you.
I think there's a question up the back there.
Hi, Lawrence Ritchie from Alpha Petroleum. I look at the life cycle of the well, and one of the important aspects is the abandonment of such an item. Has that been considered in the construction, and what considerations did you make?
It's a very good question, and my understanding is that the abandonment part has been a major concern in design, and my involvement in other technologies would confirm that as well. That what it does is it makes you think clearly about how you will abandon the well, because now we're installing them, which is the case that we're coming across again and again is when these wells that we're trying to abandon now were drilled, the abandonment case wasn't considered. So yeah, we've given that a lot of thought. I can take this offline and give you more detail if you want, but that's certainly been a consideration. And my understanding and my belief is that this aids abandonment by giving you clear thought beforehand. Thank you.
Oh, sorry, Mal, can you?
Just to clarify, Lawrence, you can remove these by a reverse of the installation process, basically. So you can pump it back out, and these have been recovered by just getting the ROV and just literally, once you've cut everything that you've installed in terms of intermediate casing strings below the can, you can then pump the can back out and recover it back to the boat and bring it back to the shore and refurbish it and use it again, which is a fundamental sort of benefit of it.
Sorry, I was thinking more of which string do you have coming out of the can? But yes, as Malcolm says, the retrieval is very simple. But I was thinking more of the how do you sever what's below the can in the case where you want to abandon. But yes, we can talk about that. But we retrieve them now on a regular basis, so for exploration wells in particular.
Any other questions at all?
Yeah. Here we have.
I'm Michi from Japan Petroleum. I didn't see the. Do you have any other option for bottom? I mean, now we are doing a soft formation. If it's like a hard, like a rocky formation to set the application, do you have any plan to do as a like a rotating mechanism or something?
I'm not aware of any plan to rotate, but we have used a jetting method in not in anger yet, but we're looking at the possibility of jetting down the inside and on the outside of the can as well, to broaden the envelope of deployment. But that's a possibility. But there's, as I said in answer to the first question, a lot of the work that's done up front in understanding the core penetration data helps in the applicability first of all, and then the deployment of the equipment. Okay.
Okay. Any other final questions for Martin? No, nothing. Mal, do you want to add anything at the end at all?
Really insightful in terms of different ways of looking at different ways to actually create that well foundation. We've supported the work that Neutral and the original C in the last year or so now with the two big projects that we talked to. And I think we've demonstrated as part of that trial that the capability is there in different soil conditions. So it gives us an opportunity for the industry and also to take the greatest practical and more robust methods of creating that well foundation.
Thank you.
Great. Well, that's us for today. Thank you very much,
Thank
Martin. For those of you that can join us next week, we are looking at data and MRS. So if you're looking to book, head to our website. You can see all our future Tech20 events on the website.